Good morning. I'm here today to talk about high-performance memory solutions. Specifically, looking at the needs of the next generation of memories and looking at the bandwidth that's required to be supported. So that's what I'll be talking about. And basically, what I'll be focusing on is looking at what OpenSilicon is going to provide in terms of the high-performance solution, specifically IP that's targeted towards hybrid memory cube. Just a little bit of background about OpenSilicon. We've been in existence since 2003, 11 years in existence. About different locations. We are here, headquartered here in Milpitas, California, and the different locations are shown there. In addition to IP, we do complete ASIC solutions. So just going on looking at the ASIC solutions. So here's a complete portfolio of what we can do from an ASIC solution perspective. So we can do all the way from specs to volume production. We can do any of these point solutions, including architecture, RTL design, design verification, physical design, and all the way into volume production. So that's what OpenSilicon does. But today what I'll be focusing on is in terms of the memory solution that we have from IP in terms of HMC. So if you look at a traditional solution that you come from the DDR family, and you look at it, it's been progressing. You had the DDR, SDRAM, going to DDR, DDR2, and now we are at DDR4. And DDR4 today is running, it's rated to run up to 3200. So 3200, if you look at it, the max bandwidth you're going to get is 25.6 gigabytes per second. With HMC, what you're going to get is, 160 gigabytes per second. So from a technology looking at the HMC bandwidth perspective, you get a 6x improvement in terms of DDR. And if you look at DDR, from DDR3 to DDR4, if you look at traditionally, DDR3 was a multi-point solution. You can go from one host controller to multiple. And you're seeing that with DDR4 now it's become a point-to-point solution. The complexity of handling DDR4 is very challenging. It's becoming tougher and tougher. And also the bandwidth that you're getting with it, like I said before, is not scaling. So HMC, what HMC does is it takes a DRAM die and a logic die into a single device, creating a new class of memory systems. So the benefits of HMC are reduced power, reduced footprint, and then in terms of bandwidth, 6x performance of DDR. So the HMC consortium, basically it's a group of companies including ARM, Samsung, Micron, SK Hynix, IBM, Xilinx, Altera, and OpenSilicon. So these are the founding members of the HMC consortium. And what they do is they develop and define the HMC specifications. To date, we have about 120 adopter members. And like I mentioned before, OpenSilicon is a founding member. We're actively involved in defining the specification and promoting the specification. So let's look at HMC technology, what HMC technology is, and what are the applications of HMC technologies. So if you look at it, what HMC does is it basically uses a 3D technology using through-silicon vias. So what it does is it takes DRAM die and it stacks it on top of logic die. And basically, it's all encapsulated into a single package. And you communicate to the HMC device using serial links, running the HMC protocol. The serial links run at 10, 12.5, or 15 gigabits per second. And each link consists of 16 or 8 lanes per link. In terms of how the HMC is going to be used, you have the traditional way where you have the host processor talking to the HMC device, like shown on the top right there, top left there. In addition, you can also have different kind of configurations where HMC can be changed. So in the bottom right here, I have a picture where I'm showing a single host talking to multiple HMC devices using chaining. Different configurations are possible where you have multiple hosts talking to multiple HMC devices, or multiple hosts talking to a single HMC devices. Now this opens up the paradigm of how HMC can be used, where now your memory can be used as a shared buffer between two different hosts. So you can do data transfer from that perspective. In terms of applications where HMC is going to be used, you're going to see wherever you need very high bandwidth, that's where it's going to be used. So what we're seeing is in terms of high performance computing, server applications, graphics, networking systems, anywhere beyond 100G or to 400G, you're going to see that HMC is where that's going to shine very well. And then finally in test equipment. So let's look at, with the current DDR technology and with HMC technology, what does it take to achieve 16 gigabytes of memory? So out here I have a comparison saying, I'm looking at a single link HMC operating at 15 gigabits per second versus a DDR3L operating at 1600 and a DDR4 running at 2133. So the first thing, let's look at the channel complexity. So if you look at the number of pins required to implement a DDR3L, it looks like it's going to take about 750 pins. So from an overall channel complexity perspective, if you look at HMC technology, it's going to be 90% simpler than DDR3, and then 88% than DDR4. If you look at the board footprint, in order to support a 60 gigabytes per second throughput, DDR3L, HMC is going to be 95% smaller and 94% smaller than DDR4 because you need multiple DDR DIMMs or multiple DDR memories in order to support the 60 gigabytes per second. In terms of the energy efficiency, what you're going to see is that DDR3L versus DDR4, it's not much different. DDR4 has gone down to a lower voltage, but it's not much of a saving. You compare that with HMC, you're going to see that it's 66% greener or less energy compared to DDR3L. And then finally, in terms of the bandwidth, if you look at it, the bandwidth that you're going to get with HMC is close to 900 megabytes per pin. So that's significant, amount of bandwidth that you're going to get with HMC. So it's 10x much more bandwidth than DDR3, and also 8x greater than DDR4. So if you look at overall cost of ownership comparing HMC with DDR or DDR3L or DDR4, you can see both in terms of the channel complexity, the board footprint, energy efficiency, and the bandwidth, HMC technology outshines the other technologies far ahead. So looking at what OpenSilicon has in terms of IP offering for HMC, so what we have is a HMC controller IP. It's compliant to the HMC specification 1.1. So what I have here is a block diagram showing the HMC. So we have support for up to 4 HMC links. The links can operate from all the way from 10 to 15 gigabits per second. So highly configurable low latency solution. We have support for multiple different user interfaces, both AXI4 and native interfaces. And in terms of IP solutions, we have IP solutions for targeted towards ASIC and also a Xilinx FPGA IP. In addition, we also have a HMC evaluation platform that uses the Xilinx Vertex 7 FPGA, and it includes a Micron HMC device, and this is readily available. So it comes with a complete set of deliverables, including a software GUI, the drivers, traffic generators, checkers, and characterization. So basically what it can be doing, the evaluation platform can be used to evaluate the HMC technology and see how you can make use of the HMC technology for your application. So what I've shown here is a screenshot of the board that's currently available and a screenshot of the GUI that's there. So finally, just to summarize, we have the HMC IP. From a HMC perspective, like I mentioned before, it's a significant leap in terms of the technology, where you get about 6x the performance of DDR4 and a fraction of the energy, and about 90% saving in terms of the board space. So for more information, you can visit OpenSilicon.com or look at hybridmemorycube.com.